engineering. I'm trying to design and build theories of quantum gravity with these new tools that we have at our disposal. So I'd like to start in that context with this beautiful picture of AdS₃ that shows us roughly how we think as a roadmap in various contexts in theoretical physics. So at the bottom of this journey, I put the theory of general relativity. So in general relativity, we think of gravity as geometry, as the shape and the curvature of space-time dictating the motion of massive bodies, okay? And this has been an excellent theory. It has made beautiful predictions. It has a beautiful mathematical description. And I have nothing against it. I love it. But I'm putting it here in the bottom because we want to move upwards. We want to learn from this theory of gravity, exception of general relativity. And as a string theorist that I am, one of the ambitions or one of the promises of string theory is that there should be a quantum version of this theory, where gravity meets quantum mechanics, where the things that are big, large, and heavy meet things that are small in size. And from my perspective, the theory that promises to the most approach that we have, it is string theory. So in a sense, when we will encounter all sorts of beasts and new phenomena, new things to describe, and new mathematics to unveil, will be up here. And so this colloquium is basically the journey from going from the bottom from the bottom to the top, and also we'll be going from the top to the bottom. But I will take, and in that context, and trying to basically connect these two things, I'll be a little bit more agnostic, so I'm not just going to talk about general relativity as a theory by itself, and not just think solely in terms of string theory. What I want you to think is that we will have a low energy description of a gravitational theory that could not just be general relativity, but it could also contain matter fields. So we will have some low energy description, which we will think along these terms. And the question is basically, how do I go to the top? And so the two main questions that govern this talk are basically, what are the set of basically effective field theories, so these low energy descriptions that are meant at UV completion, that you can nicely and consistently go upwards. And so that usually goes under the name of the landscape. What are the set of theories that are consistent? And the second question is basically, from the bottom to the top, and from the top to the bottom, and that will tell us about what are principles and laws in trying to understand a theory of quantum gravity. Okay, so that is the landmark. Now, in that process, today I'll show you how I'm thinking about this using three basic tools. So they bring us up in different levels of complexity on how do we reach this UV completion. So the three things that will be prominent and that have influenced this work starts basically with black holes, the holographic principle, and low-dimensional models of quantum gravity. So let me motivate a little bit each of these three key points before we start. So the first one, black holes, unfortunately, despite the fact that I'm mentioning here, there will be the least prominent. This is the only time that I'm going to mention black holes, and then they might come up in questions. Please ask me, but they're always part of the inspiration. They're always leaking in the background. Even when I'm not talking about black holes, they're there. So therefore, here they are. And the thing that we love about black holes is that it's truly like the first type of phenomena where you see that the quantum meets the classical, where you notice that general relativity wants to be described in terms of the quantum world. And the most famous incarnation of that is the Bekenstein-Hawking entropy formula, okay, that tells us that black holes carry information. There's microstates inside of them. Although I never advocate to taking a journey into a black hole, I've heard that it will be quite an interesting thing to do, but not advised at this moment. But okay, so this is basically the lamppost of black holes. Now, in connection to the holographic principle, and one of the reasons why I wrote this formula. So this formula has a lot to teach us, but one of the things that it taught us after a few decades that it was conceived is that the entropy, so the amount of information that you have in the system, is something that doesn't scale with the volume of the system, it scales with the area of the system. And this was one of the precursors of how to think about gravity in terms of these holographic terms. And we'll go more into this. I'll tell you more about this holographic way of thinking about gravity, but basically it's very nicely connected with the physics of black holes. And that's why they're lurking in the background as I go through this. Now, finally, there's these low dimensional models. So I'm not going to talk about gravity in 3+1 dimensions. I will be talking about gravity in 1 dimension lower. And I always feel like I have to say something about why. Why would you do that? And I think from a mathematical point of view, and as I will illustrate today, it gives me quite a lot of precision and control. So I'll be able to report on results and tell you things that are concrete and sharp. But more broadly, one of the things that I do want to highlight that will not be addressed in the colloquium, but to keep you in mind, by the study of low dimensional models, eventually with time, they do trickle into teaching us about physics in our 3+1 dimensional world. So for instance, one of the things that has been quite prominent in the past year is how the understanding of gauge and asymptotic symmetries in low dimensional models has made it at the forefront in 4-dimensional physics, where it has impacted our understanding of scattering amplitudes and understanding soft hair theorems and other type of phenomena observables from a 4-dimensional point of view. So from that point of view, I feel there's quite a lot of motivation from different perspectives of why we do study low dimensional models. But okay, in any case, what we're going to do today, we're going to look at these basically 3 components with the 2 questions that I presented to you at the forefront and trying to understand in this context of using holography, of using these low dimensional models, how can I address questions about what does it mean to go from the bottom to the top. And the mathematical tools that I'll be using, unfortunately I won't be able to describe them in details, but the mathematics that goes behind this, there's a beautiful story of modular forms that has impacted a lot on how we can be precise and how can I report results to you. We use very extensively supersymmetry. That will be very obvious at some point during the colloquium, the role of supersymmetry, and then the role of conformal field theories. So theories that are invariant under dilatations. Okay, so these are basically the 3 key concepts at the technical, like mathematical level, how things are impacted. Yeah, so we'll proceed. And I do want to say, if you have questions, I know this is somewhat more of a formal setting, but I don't mind. Please interrupt me, ask me questions if something is not clear. There will be very few equations, lots of pictures, cartoons, silliness from the speaker, but please, if you have anything that you want me to elaborate further, don't hesitate to ask. Okay, very good. So the colloquium will be divided into 2. I'm hoping the first part will give a bit the bigger picture. I will describe the setup. The second part, you might feel free to fall asleep. So it will be more on the technical side, showing explicitly what have we achieved at this last point. So in the first part of the colloquium, I want to take this holographic perspective that I mentioned at the beginning very, very seriously, okay? So I will explain what this holographic perspective is, but this is going to be the way how I'm going to have blueprints and I'm going to have designs that will tell me what does it mean to have a theory of quantum gravity. Okay, so I'm going to be exploiting that principle to a great extent. And with that, what I'll show you how can we basically understand what is the space of UV completions of quantum gravity. Now, in the second part of the colloquium, it's more focused on the work that I've been doing in this past years, and it involves the subject of symmetric product orbifolds. And from this engineering perspective, this is going to be my materials. Okay, so this is I'm going to use a class of theories and able to try to answer these questions. So I will have constraints, I will have restrictions based on these blueprints that I'll explain, and then within the setup of symmetric product orbitals, we'll get our hands dirty and we'll start building, okay, and we'll see. It will be a specific setup. It will have some limitations and some restrictions, but it will show us how can we move forward. What does it mean to proceed? And what does it mean to answer this question from this holographic point of view? And I want to highlight here, this has been work that we've been doing for quite a few years. There's various collaborators, many papers with all the equations and mathematics and physics needed. But I do want to highlight some of the youngest people in the collaboration from the past years because I'm very impressed with them. They've been excellent at this work. And if you wanted to hear more about the technical details, you should definitely invite them because, yeah, they have surpassed me also and the understanding of many things. And so in particular, I want to highlight here Susana Ventaya. She's my PhD student. She's still in Amsterdam, halfway through her PhD. She definitely knows way more about symmetric product orbitals than I do by now. There's also Yilda Hollander. She was a master's student at the time that we wrote this paper. Very impressive. She's now started her PhD as well. And Luisa Bono, who's a postdoc in Amsterdam, who also has been wonderful to work with, excellent collaborator and researcher. So all of my collaborators are amazing, but I'm just trying to highlight some of the most junior ones in this endeavor. So keep an eye on them. They're really excellent researchers. Very good. So I hope we're ready because all this expectation was building up. Now we have to get going. Okay, very good. So let's engineer this theory of quantum gravity. So let's first talk about what is this holographic principle? How am I trying to engineer this? What are all these words that have been thrown around to you with little context? So in this modern era of thinking about gravitational physics, the way that we're thinking about gravity nowadays comes with this proposal that a gravitational theory that lives in d+1 dimensions is equivalent to a quantum theory living in one dimension less. Okay, so the usual pictures that we draw in trying to illustrate this duality, this equivalence, this correspondence between these two frameworks is that we have a gravitational theory living inside of a volume, and there's a boundary or not necessarily a physical place, but basically there's a quantum theory that lives at the edge. So we usually draw it explicitly the boundary where the quantum theory lives. And this quantum theory here does not have gravity in it. So it relates basically two systems that are seemingly very different, but this is basically the proposal of the holographic principle. You can also think of it in terms of a can of soup. I love the can of soup analogy. Do you guys know the can of soup analogy? No? So, the can of soup analogy. Okay, let's talk about soup. I did have lunch, so I'm not hungry, but
mold growing.
What's that?
It's not about mold growing.
No. No, it's a really deep thing. You will not be impressed when I explain to you the can of soup analogy. So the can of soup analogy is that when you go to the supermarket, you want to buy soup, right? Because you want the stuff that is inside of it. When you go to the supermarket, don't open the can and try it, right? That's not what you do.
You just look.
You look at the label. So all the information about the super side is written outside of the label. It's really done. Mario got it. That's it. Like, so all information is included in the label. It's a very basic analogy. But okay, but that's it. Because I really hope that none of you, when you go to the supermarket, you open the can of soup and try it to see if it's tomato or whatever.
It's still your disappointment.
Well, I hope this will be fantastic soup. So in this analogy, gravity is the soup, and this field theory that it's in the edge, this quantum theory at the edge is the label. Okay. Yes?
I'm not a high energy physicist or anything like that, but in statistical physics, we have this similar thing that a quantum theory, which lattice of d-dimensional can be described by a classical theory in d+1 dimension via product formula expansion.
I see.
So is that the same, essentially? Because in some sense you're looking at the quantum theory in one dimension less, something classical in the higher dimension. Is that the same?
I'm not familiar with the correspondence that you're describing.
If you have an exponential of the sum of non-commuting operators,
Yeah.
of quantum mechanics, then you can have under certain condition, you can expand that by introducing a second dimension in terms of a product, so-called product form.
I see. It might be similar. There will be some, as I will explain, there's a few features of this correspondence that make it quite interesting. But yeah, in the sense, so let me, yeah, because again, since I'm not familiar with this, but I'm like in many cases, like I'm not going to say that this like dualities or equivalence between systems. It's not necessarily special to gravity per se. So you can also have instances of this with matrix models, for instance, or other types of systems. The thing that is useful about one of the reasons why this got a lot of hype is because we tend to not, there's certain contexts where we're not very good at gravity. And so mapping it to a system where we feel that we have more control brings this utility. So, but yeah, but I'm within the realm of like mathematical physics. Yes, there's various forms of other types of dualities. This is the one that involves gravitational physics, which is, and it's quite surprising that this theory here on the top does not contain gravity. So that's the power of the correspondence. So it relates something that seems very, very different from the original conception.
Your gravity is quantum gravity.
Well, it can also be classical here. But the thing is that it gives me the tool so you can have something classical here, and then it will be quantum here, and vice versa. So this is where I'll describe what the couplings are doing. So, but in potentially, you can also put here quantum, and then it gives you a lot of control of what you mean of quantum gravity coming from the top perspective. So there's various knobs that you can tune in this correspondence and change a bit what's happening here and what's happening in the bottom, and it gives you this flexibility in the correspondence and how these systems are mapped in a dynamical sense. So very good. So the jargon a bit, this is going to be very quick. So we usually refer to the gravitational theory as the bulk theory, and the boundary, this quantum theory as the boundary. Very good. Now, the setups where we have a lot of control on this, it's what goes under the name of the AdS₃ correspondence. So let me say a few words about that. So the AdS₃ correspondence, it was where the principle and this holographic principle was first established. It came from, it was born and refined in the context of string theory. And in this setup of the correspondence, basically this gravitational theory here living in the middle is characterized by having a negative cosmological constant. And then this quantum theory at the edge it's a conformal field theory. So it's basically a theory that is invariant under dilations. Okay, it's scale invariant. Very good. So this will be also the type of correspondence that we're going to be studying. Now, one thing that I wanted to highlight about this correspondence is that it maps couplings on both sides. So in particular, the way that couplings are mapped here, and this will be, for instance, important. So for instance, if this conformal field theory is very weakly coupled, so you think of it perhaps in terms of free theory, where things are not talking to each other, then the theory of gravity in the middle will be very, very quantum. Now, you can also do the opposite. So you can say, let me crank up couplings in this conformal field theory and make it very strong coupled. Then the theory here in the middle will look more like general relativity, will look like gravity as we're used to. Okay, so this is one of the strengths. This is one of also, you can see it as an abstraction or as a feature, depending on the day of the week. But basically, this is one of the characteristics of this correspondence. Very good.
So, in that analogy, so you're starting with if you're moving from the weak cupping limit to the strong cupping limit, you're moving manifold.
And I'll draw you a beautiful conformal manifold.
Yeah, now it's what the conformal manifold was.
It's an excellent question. We'll get to it. I'm not going to fully answer it, but basically, yes, you're thinking that you have a conformal manifold where you can change the values of these couplings. Not all instances of holographies have this feature, but definitely this is going to be a feature that I'm going to be quite a lot. Okay, but what I want you to remember about this is that it's a duality, so it really tells me how to map quantities on one side from the other one. And what's very, very important for me is that it's a framework. It gives me a definition. If I take this correspondence at face values, it gives me a definition of what quantum gravity is. And I'm going to take this quite seriously. Okay, so I'm basically going to define gravity and quantum gravity by this system. Okay. Now, in this context, what I want to, like, given that you want to understand more this correspondence, what is its origins, how does it work, when does it work? There's various types of questions that you can ask. Okay, so in understanding, like, why did it came about? Why should I believe this? Why is this a useful way? How to think? So here I listed some questions that you can ask about this correspondence. They're not the only questions that you can ask, but some of them, but like, what's going on? So one question that you can ask, so you can say, okay, if you take this point of view very seriously, that this theory at the edge is going to define for you gravity or quantum gravity, one approach you can take is like, okay, I give you one of these conformal theories, tell me what the gravitational theory dual to it is. In principle, this is possible. It is something that I have worked in the past, but I'm not going to focus on that question here. And I'm happy to talk about it more if we have time afterwards, or yeah, during the rest of the day. The second question, which actually is going to be quite the focus, is basically saying what I want to ask, because I love my theory of general relativity. I want to ask the question of, okay, which of these theories here can tell me something about classical gravity? Okay, so what do I need at the edge such that the thing here in the middle looks like general relativity? Okay, so that's what I mean by the sentence. Which classes of conformal field theories can capture classical geometrical properties of gravity? Now, the other approach that people have taken, which is a little bit the counter of the second approach, is say, fix your theory of gravity, insist that it has to have a dual, and then tell me what the properties of the dual of the boundary CFT are. That's a different approach. I'm also not going to take that third approach. And I'm also happy to talk about it during the questions. You can ask me about this one. We're going to focus on the second approach. Okay?
But not like any CFT has dual quantum gravity.
It depends on
define quantum gravity as dual CFT.
The AdS₃ model has a dual that looks like quantum gravity.
Yeah.
It's very, very quantum. And then regarding the question I had in the back, you can't tune the couplings and you're very constrained. So you won't have, so if you grab a CFT, there will be various aspects that you will be able to map to something that looks higher dimensional, but you might not have the parameters such that you can say it has a semi-classical description. So that's an abstraction. So for instance, for the AdS₃ model, that's something that we did. We said, okay, just grab the AdS₃ model in 1 + 1 dimension and tell me which way does it look like gravity. And you can organize the theory such that it looks gravitational, but it doesn't have a limit where you would say this is general relativity. So it has a very, very quantum feature. But now, of course, you can say, well, then you have to refine what does the AdS₃ correspondence mean? Like, is it always an equivalence, or what are the restrictions under the equivalence? So in trying to understand also part of the mechanism is like refining what the correspondence means, and in which cases it's a well-defined consistent correspondence, or where you're like, no, this doesn't apply. So that's part of what these questions are trying to address. Like, what are the rules of the game? What does it mean for you to relate these two systems? And in which way this is a useful relationship or just a formal relationship?
Like in technical terms, it's only like a few CFTs that has this feature that you have decoupling of classic mode.
Yes, exactly. And those are, so my second question is trying to capture those types of instances of the correspondence, not a generic instance of the correspondence. So the first one will be more like a generic instance, and then the second one will be more along your lines of like, yes, I want to have some low energy sector that is decoupled, and I don't have to like look at everything else. So really having an effective description. Yeah, these are all excellent questions. Very good. Running short on time. So with that in mind, sorry, I was going to say, so I'm going to focus on this dimensionality of AdS CFT, and I will take at heart that a two-dimensional, a 1 + 1 dimensional conformal field theory will define for me this AdS₃ gravity. Now I should tell you a little bit about what this AdS₃ gravity is. And this is the next slide will be the only slide where I write something gravitational. And then the rest of this colloquium will, whatever I have time to say, will all be about conformal field theories and understanding the space of conformal field theories. So just to have a bit of intuition of what's happening on this gravitational side, what I have in mind when I say AdS₃ gravity is that I will have an action principle, which will contain a sector that will look like the Einstein-Hilbert action. Okay, so we'll have this form. You have the curvature and the negative cosmological constant here. And I will also allow this theory to be coupled to matter. So you can have bosons, you can have fermions, you can have gauge fields. And I'm not writing explicitly what type of matter I will have because this will be part of the outcome. Okay, but this is basically what I'm thinking. And the basic requirements of what I'm looking for in my, as I try to understand how to build this correspondence and have a definition of gravity from the CFT, I hope that one of the outcomes at the end is that this resulting theory looks like a local effective field theory. A local effective field theory means that there's a regime in which it's meaningful to write down this answer. Okay, and then think of like, oh, you will have corrections, so this will be the semi-classical description, and then here you will add ... as corrections that come from semi-classical description. Okay. Now, one of the very universal entries when people studying holography in this context was that they related the Newton's constant and this cosmological constant, the AdS radius, to the CFT via its central charge. So the conformal anomaly in this two-dimensional system. So if we want this description to be true, there's this relationship between the couplings. So this is a coupling in the CFT. These are couplings in the gravitational side. And this expression is valid if this number is very, very, very big. Okay? So this automatically forces you, if you want to land in a theory that looks like this, one of the basic requirements that you have is that the central charge of this conformal field theory has to be very, very, very big. Okay? So these are basically some of the minimal inputs that you need for the correspondence to work and to basically land you here in this beautiful geometrical description of gravity. Very good. So let's talk about CFTs. Let's talk about conformal field theories in 2 dimensions. And I draw a circle. So imagine this circle being the space of all conformal field theories that are unitary. I'm drawing a circle, and it's actually, well, think of it full. I don't know, I should have colored it. But let's imagine for a moment that you know all the space of conformal field theories in 2 dimensions. We do not know the space of all conformal dimensions, all conformal field theories in 2 dimensions. But let's imagine that we do. And what I want to do is define gravity via the conformal field theory. So in some sense, what I want to do, if I know this universe of theories, what I want to carve out is which of these theories has this holographic content, this holographic features. Okay? So out of this whole set, I want some subset for which they answer the question, can you capture classical geometrical properties of gravity? Okay, and that's what I will be calling throughout a holographic CFT. I'm abusing a little bit the terminology, but I do want to be very clear that during this talk, when I say holographic CFT, I mean that the counterpart, the dual, will have a classical feature. Okay, and again, the sizes here of these circles mean nothing because I don't know the first one to start, and the second one is part of the work in progress. Okay. But we want to understand the space of control. Now, what I have told you so far is that in order to at least define this darker circle, I need at least 2 things. So the first one that I mentioned in the previous slide is that we need to look at the space of conformal field theories for whose central charge is very, very large. The other requirement is what I'm calling here and being quite vague is that you have very, very few states. This basically comes about, if you solve for this theory of gravity, there's certain solutions, basically this AdS solutions and this set which are black hole solutions. And if you look at the spectrum of this theory, what makes it low energy and effective is that there's very few states between what you would have called the vacuum state and the first black hole. So there's more refined versions of what this means, and I'll bring them in as they're needed, but basically this is what I mean. Okay, so the theory is it's perturbative around the vacuum solution, and then at some point you start having black holes in the spectrum. Okay, so that's what this comment means. Now, many of these features here will imply, for you to have this low energy description, that the CFT is strongly coupled. Okay, so that's also what makes it very difficult to define this circle. The theory is strongly coupled. And here comes my moduli space. So I was asked if there was a tunable parameter. And yes, there will be a tunable parameter because describing strongly coupled theories, so these theories that are supposed to be holographic, is not an easy thing to do. We still don't have all the tools and the ways how to describe them. So what I will think is that this strongly coupled theory is one point in a moduli space, so in a space of couplings.
Why? So the thing that makes you strongly coupled is the fact that you have large center charge of two states. Because the large center charge by itself should.
No. The large, that's why I put it like in bracket. Like there's a collection of things, of phenomena that will tell you. This will tell you that the theory is strongly coupled. It's not one individual one. Like yeah, you can have theories with large central charge that are still weak, and I'll show you in a moment.
But those ones have many states.
Yes, those have many states. But then it's always a confabulation of like different requirements that then will tell you, if you want to meet all of these criteria, the theory cannot be weakly coupled. The most natural one that tells you it's strongly coupled, it's not like we prove it in a very rigorous way, but like the sparseness, this very few states condition, usually indicates to you, you have to add a coupling there. Because if you have a free theory, they have too much stuff. Even if you gauge it, like you need to start like removing states and try to either lift them or make them massive somehow, like very
Yeah, I'm not sure whether certainly weekly coupled.
Exactly. So they will not meet this like this light, nice little spectrum that I wrote. So that we know, and so yeah, and then in very explicit versions of the duality, as you know, it is strongly coupled. Now, so from this perspective, this is how I'm thinking. These holographic CFTs live at a strongly coupled point, but then I have a set of couplings in the language of the conformal field theory. This means that you have exactly marginal operators that if you turn them on, they make the conformal field theory still be conformal, but they're just changing the values of the couplings. Okay, so that defines for me this moduli space. It's the set of exactly marginal deformations. And the word exactly here means that the operator always remains marginal, so I'm not worried about the existence of this moduli space in the set of couplings.
You're not claiming that for each one of those there exists an exact region. I mean, that's, you're restricting further.
No, I'm further restricting because I'm trying to, because I'm trying to do something interesting about what is the space of conformal.
That's pretty special.
You will let me know at the end of the colloquium.
We're going to have symmetry for the.
Then there's n equal 4 superior.
Yes, when you then equal 4, then it's basically.
Yeah, and there's two marginal deformations. One is single trace, the other one. And then if you have less supersymmetry, then the conformal manifold is more. And you can have more direction in conformal manifolds.
But it could be special in the number.
If you talk to someone doing swampland, a lot of the things that they say do not apply to 2D, so in that sense they're special. Because in 2D you have, it's very easy to get higher spin symmetry. So a lot of the things that they conjecture and they wave their hands about what this space looks like, because this is part of what their landscape is, they don't apply to 2D. They're upfront about that, they know that. But so stuff about the conformal manifold that they conjecture in higher dimensions does not necessarily apply to 2 dimensions. So what I'm going to do basically I'm going to think that within this moduli space, I'm hoping that there's a point that will look weakly coupled. And here I will have much more control. And then basically what I want to do is establish that I can deform the theory and get to the strongly coupled point. So that's what we're going to do. And so what from the weakly coupled point, what I'm going to do is basically, as I said again, so I'm going to again have a large central charge limit. That's fine. But from the weakly coupled point, I have to determine that there is a moduli, that this cloud exists, because these guys are exactly marginal, so you should see them at every point. And there's various quantities that are protected here, and this is where supersymmetry will enter. Well, it also enters in the statement of exactly marginal, but basically there's various quantities that are protected under this cloud that are independent of the couplings. So if I compute them here, I should already have signals that the strongly coupled point exists. Okay, so these things you can use to test the existence of the strongly coupled point. So these will be the three basic ingredients that we'll be using to establish that this point exists and that it meets the criteria here. So it's a little bit of a roundabout way how to do things, but these are the tools. This is what we know how to basically do in this type of setup. Okay, so how much time roughly? What is the
20 minutes.
20 minutes? Okay. Yes, I probably will not have time to go through everything, but it's okay. You'll ask me tons of questions afterwards. Very good. So let's talk now about symmetric product orbitals. So we have our setups. So just to maybe flush it again, like that. These are my rules. This is my blueprint. Okay. This is kind of what I want to try to achieve. This. Very specific design, but I love it. Don't judge it. You can judge it. It's okay. Okay, so let's.
Yeah. A question about the so you're going to start from the big CFTs because they're easier to deal with, and then you want to detect the point for the strong. Exactly.
So we're going to start here and impose these restrictions and see how much evidence can we get that this point exists.
So, sorry. And here we are not thinking that the weakly coupled CFT is defining like the really quantum phase of the.
It is defining the very quantum phase of the theory. Yes. Yeah. It will. It will define, in principle, if this whole thing is successful, it will define for me some string vacuum that has a lot of symmetry, and it will have potentially it should have like a world sheet description and all the bells and whistles. Okay, so this horrible word, what is symmetric product orbitals? Who knows? Okay, so very simple, short description of what a symmetric product orbital is. Do not be afraid. It's a very, in words, it's a very simple system. So what you're going to do is you will pick your favorite CFT and tensor it n times. Okay, repeat it. Now, if you do that just by itself, if you just tensor it, of course, this thing has a permutation symmetry. You can move the copies around and you will get the same thing. So what you do in a symmetric product orbital, the definition is that you mod out by the symmetric group. So Sn here is the symmetric group. That's a symmetric product orbital. Okay? So it has many words and it sounds scary, but this is at its core. Okay, tensoring a theory and modding out by the permutation group. Now, one of the features, this will be a bit of jargon. So once you have this structure, so this will be this type of conformal field theories that we'll study. You have two types of states, what we call untwisted sector. This means that there are states that are invariant under the permutation group. And then you have sectors that are called twisted, which basically means that you label them by the conjugacy class of the permutation group. Okay. Now we're all experts in symmetric product orbitals. Yay. Not excited. Okay.
Non-trivial conjugacy.
What's that?
Non-trivial conjugacy.
Non-trivial conjugacy.
Can you maybe elaborate the gauge theory analogy to the twisted sectors?
To the twisted sectors. Yeah, it's in the gauge theory analogy, like the gauge invariant operators are the ones that are in the untwisted sector. The twisted ones, I don't know if I have a good analogy off the top of my head. I would have to think about it. Maybe if someone else in the audience is familiar with it. But yeah. But usually when people tell you like, oh, the modding output, the symmetric group looks like a gauge theory, it looks like gauging, it's because of, yeah, that you're basically removing, the untwisted sector looks like basically the gauge invariant operators. Yeah. But it's not quite a gauge theory, so that's why the analogy kind of like stops at some point.
The symmetric product of the flow, so the spectrum is the same as in each copy, it's just like multiplicity stuff.
Each copy is the same, it's exactly the same.
Yeah, but after you.
But then after you do, then you will have, when you organize the partition function, I removed the slide that had the partition function, then the partition function will have it will have contributions from this untwisted sector. So it will look like, for instance, an untwisted sector will look like you put the same operator in each copy and then sum over it. That's an untwisted operator. But then you also have twisted sector states. So the partition function has like more, it has different types of states, the untwisted one and the twisted one.
So twist ones, you have to complete them.
Yeah, they arise, so the twisted operator is basically a boundary condition. That's how you think of it. So it means, so let's say that so this is the complex plane and then you go around. So yes, it's exactly, it's a twist operator. Yes. So it means that, so untwisted means that, oh, if you go around the complex plane, you get to the same point. Twisted sector means if you go around the complex plane, you land in a different copy. So it's a boundary condition. So it's the same operators, but you're allowing for the operators can be non-periodic because they can basically move to a different copy. And if they do that, then they correspond to a twisted operator. Okay. Okay. So what we're going to do, I'm sorry, I went too fast because I was talking. Yeah. So you were asking me about this, and then we went here. And so you might ask, why in the world should we study these theories? So historically, they have a lot of appeal. So these theories, they're theories that have a lot of mathematical control. Okay, there's a lot of analytic control. There's a lot of things that you can do. One of the my favorite formula in this context, it goes under the name of the Dijkgraaf-Moore-Verlinde formula. That basically is the generating functional for the partition function of a symmetric product orbital. This is where modular forms enter in our analysis in computing the partition functions of quantities. It's very familiar in string theory. So the most famous symmetric product orbifold is the symmetric product orbifold of 4 or K3. In the string theory context, this comes inside of the D1, D5 system. It's universal. I will highlight this a bit more. And then it has its utility. So these two things I'll tell you about in the coming slides. But what I want to tell you today is about non-universal properties that the symmetric product orbitals have. So if you try to classify them in this endeavor that I have of the cloud and the circles, remember the clouds and the circles? In that context, not all of them behave the same. There will be interesting patterns, and there will be some things that I'm a little bit afraid of. So I'll share them with you. So you can tell me, Alejandra, don't be afraid. It's okay. Spooky. It's really spooky. Kind of scary. Okay. So what are the universal aspects? Why are these theories receive so much attention? Well, they comply with large n factorization, so just as by themselves. So if you look at the structure of correlators and take a large n limit, they comply with this. This is quite a while. If you look at thermal properties, so this is correlated with black hole physics, symmetric product orbifolds have what's called the Hawking-Page transition. So this relates to the physics of black holes when you interpret them holographically. So this doesn't matter which theory you put here, these statements apply. Now, what's also very generic is that you can have higher spin currents in this theory. Okay? And the perturbative part of the spectrum is Hagendorn. So in that sense, it looks like a weakly coupled theory. You have tons of states. You have an exponential growth of states. So these two first features are great. You would say from here, these are features that are very appealing from the point of view of AdS₃. These two last features, I don't like them that much. These are things that I want to get rid of. This is what I will denote these theories by looking like a weakly coupled theory, where you have lots of symmetry and you have lots of states. They do not look like this semi-classical theory of gravity, okay? So usually when people try to interpret this theory by itself in terms of a dual, it will look like the tensionless limit of a string theory or a higher spin type gravity. Yes?
Could you just say again what how the dual group?
It means that you have exponential growth. So it means that the number of states that a given energy goes like the exponential of the energy. That's the basic. There's more to it, but that's in the sense that I'm using it here. That there's an exponential growth in the number of states. And these are states that are perturbative from the point of view of distinguishing between perturbations close to the vacuum versus very heavy perturbations that will look more like a black hole. So this growth is in the perturbative part of the spectrum, not in the very heavy, like black hole-like part of the spectrum. It's exponential. Hagen-Norm equal exponential. Yeah. So going back to this picture here, so I'll think of this metric product over the weak point, and we want to basically ask. Basically, the first question is like, if you start with this weakly couple point, does this strong couple point exist? Like, what are the requirements for which given theory C here does this picture make sense? Does it make sense for all of them? For some of them? For only our favorite D1, D5? Like, what is the story here? So for which classes of theories C, this is the right way how to think of that.
You can answer first for which one that we had an exact dimension.
Very good. We'll ask that.
Oh, good.
Good. So basically we want to see the intersection. If you start with a supersymmetric theory that is a symmetric product orbifold, in which way can we connect it to something that looks? So very good. So what I'll do, now I'm specifying here, I'm going to look at symmetric product orbifolds, and we're going to determine which of them have a deformation, and for which of them the spectrum, the BPS spectrum, which is this protected quantity.
So you're also saying supersymmetry.
Yeah, because otherwise I don't know what these two were. So, well, first of all, I don't know of any conformal manifold that is not supersymmetric. Not because they don't exist, I just don't know of them. I don't know how to define them. What's that? For what?
For unitary.
Yes, I am considering this as a unitary CFT. No, because I want the operator to be protected. So I want it to always be marginal. So of course you can have marginal operators and things that are not supersymmetric, but there's nothing preventing them from receiving an anomalous dimensions themselves. And so they can start running around. So if I have supersymmetry, then I know that if I establish that the operator exists here and it is supersymmetric, then it's protected throughout. And then I want this, and then you know that there are other protected quantities that you can test. So this is where I land in the supersymmetric land. So with that, then we're going to impose these two criteria. So I want the existence of a suitable moduli. In particular, I want it to be single trace, twisted, and supersymmetric. I can say more since I'm running a little bit short in time. I'm not going to explain why I picked those three things, but you can ask me later. And we're imposing this sparseness condition of liquid genera, which basically captures this BPS spectrum. And in a very basic classification, if you have two criteria, then there's 4 options, right? So you can either meet both criteria, you can only meet the first one, you can meet none, or you can only meet the second one. Very basic classification based on these 2 criteria. So there are things that we can compute and quantify very carefully. So the result, I want to tell you a little bit what you can say before putting theories into buckets, what you can say without doing much work. The first one is that here I put a C naught just to illustrate that I'm not talking about the whole CFT, but I'm talking about conditions on one instance. So as you look at these 2 criteria, and you want to see, okay, when does this theory meet these two criteria? There's restrictions on the seed. And the first restriction that you will find is that these two criteria will not be satisfied if the seed central charge is bigger than 6. This already puts a very, very stringent bound. So I don't have to study all theories in order to meet these two criteria. I have to study theories within this window. The second one is that this criterion 2, the reason why we picked it, is not just because it's supersymmetric, but it's because we can actually solve it. It's very systematic, and it comes from the powerful theorems and methods within number theory of how you manipulate modular forms. So this is something that you can just go through the entire classification. I'm not going to leave anyone behind. And the third thing that I want to say about this criterion is that one of our results was that when we looked at it, one thing that we proved is that if this criterion 2 is satisfied, so if you notice that the theory is sparse, then instead of going like, so the generic behavior is like e to the delta, so this is the Hagendorf growth. But if you have something less than that, then it always goes like a square root. So this is already sparse in our notation. But this is basically the only way that you can meet criteria 2. If it goes like a square root instead of linear with the parameter. So now the classification, I can tell you so far what we have found. So there are theories that meet both criteria. That's great. There are many of them. There's a whole class of them, but we call them needles because it did take quite a little bit of work to find them. And this is because actually these two types of theories are very, very prominent. If you just look at it from the point of view of modular forms. So if you look at it from a number theoretical point of view, these two classes are like very, very much populating the whole like classification. Now, this type 2 here is kind of interesting, and this is the one that I'm afraid of. This other type of theories that have Hagendorf growth, but there is a moduli space. And I'm terrified of them because they like to mimic these ones on top here. And then this third one is a boring generic one. So this one's like there's tons of these theories of them, many of them. And then the other thing that is interesting here is that you might think that there's theories, for instance, that are sparse. So they meet this, they comply with the criterion 2 and the sparseness of the BPS spectrum, but they don't have moduli. Those theories, we haven't found a single example. So there's some unicorns in our classification, and it's kind of interesting. So basically what we're seeing is that every time that you meet the sparseness in the BPS spectrum, then you have moduli automatically. We haven't been able to prove it, but it seems to be that's the pattern from the classification.
Those are all rational?
No. So let me, sorry. Here there's one of the ones that I hate. This is the scary one. Since I'm running short on time, I'll skip this. So let me show you how the classification looks as a value of the central charge. So when you are between 1 and 3, these will be Virasoro minimal models. And they're all type 1. So these are the rational CFTs, and this is when you have supersymmetry. But then we also looked at ranges between 3 and 6. They're not rational theories because the central charge is bigger than 3. And in that case, you have all 3 classes. And then if it's bigger than 6, as I explained, then none of these are going to be holographic. So basically, the only range that is interesting is between these two. Now, the last thing before I conclude, so here, for instance, I just emphasize a little bit more on this Virasoro minimal models, just to show you this is how our moduli space looks like. So you have different types of theories, A, D, and E in the minimal model classification.
Sorry, the minimal model is the C? Or
It's a C. So like you put an A, and you tensor the A n times.
So the central charge is whatever.
Yeah, it's like
C times n.
Yeah, this value is 3k divided by k plus 2, and then you multiply it by n, and then you make n very large. Yeah, so you're doing literally, yeah. But then you can describe, like this moduli, so here we're listing what the moduli is, so there's different kinds of them. And what's fun about this table, the only reason I wanted to show it, I'm about to finish, is that, okay, so you have these ones that are single trace, twisted. So these are the ones that break the higher spin symmetry. This is the thing that's going to make many, many states massive, ideally. That's the lore. But the thing that is fun and that is new about these examples of holography is that you can also have multi-trace deformations, like triple trace or higher. And this is what we're investigating right now. These multi-trace deformations are not very common in higher dimensional forms of the correspondence or in the two-dimensional form. We've only seen papers that have double trace deformations, but not triple trace or higher. And the fact that they exist tells you that you can turn on couplings now on the gravitational side, and you can in particular have gravity coupled to strongly coupled matter sectors. So this is a way how you can, for instance, couple gravity to something that looks like QCD. So this is what we're trying to do now. So they're the first examples of CFTs where you have this type of multi-trace. So with that, I have 1 minute left. So let's conclude. So I told you, I drew a lot of circles for you. And so here there's a few more circles for your enlightenment. So what we were trying to do is basically try to characterize the space of conformal field theories and see which of them meets this holographic criteria. And what I want you to keep in mind is that this is something that you can answer. Okay, it's not for all the space of conformal field theories, but even if you put limitations, there's interesting answers, and there's interesting different types of theories that you can quantify. So and one of the things that we're learning is that they tend to have different properties from known examples. They're very systematic and tractable, and there's also infinite families within this classification. So it shows something else as well about the uniqueness. And with that, I'll leave you with my journey of trying to go from, well, the bottom from the top from the bottom. And here I'm just listing again, so what are some of the questions that we had? What would be some of the next steps that we have in this way of understanding gravity, of engineering gravity, purely from a formal field theory? How would that look like, and what are the conditions that you need? So with that, I'm done. Thank you.
You were checking the furnace of processedness of BPS. Does that guarantee that the non-BPS part will have the same requirements?
No, they don't. So the non-BPS part is always Haggaker, and it's not protected. So that's why also at the beginning I said asymmetric product overflows are always Haggaker, and it's because if you look at all the states, there's too many of them. And so then what the moduli does is basically make sure that those states that are not protected, they acquire mass, they become heavy. But then the protected ones will continue to be light. They will be protected in that sense, and that's why we need them to be sparse, because you know that even if you turn on a coupling, they're still going to be there. So we have to make sure that there's not many of them as well. But the thing is that not every supersymmetric theory is sparse. So not just because you have this index or thing, it means that the thing has a nice behavior. No, you can also have horrible behavior in that sector, and that was the first way how we discriminated. And we noticed, oh, there's something interesting to say in the space of theories. Not just because you say symmetric product overfold and because it looks similar to the 1D5, it means that everything goes. No, there's actually criteria that you have to satisfy. There's restrictions that you have to put in. And then you get different classes. And then the moduli was a further restriction. But yeah, that was putting it in there. And yeah.
But they still need to ensure that unprotected.
Exactly. So that's why I cannot prove that the strongly coupled point exists. I only have evidence towards it. So we're trying to come up with more. So part of the endeavor here is like saying, did I just impose sufficient conditions? Or like, yeah. So I'm imposing things that are necessary, but I don't know if they're sufficient. So that's the name of the game, because if these are sufficient conditions, they will be quite powerful. It will tell you something very important about how theories respond, telling you like, if you impose these two things, then everything else that you love about AdS₃ will come for free. It's not clear to me, but understanding what is a set of sufficient conditions, at which step you say you have enough data to establish that this strongly collectible point exists, that will be fantastic. And I think it's doable. So I'm hoping that it's my head. This is my dream. This is what I dream about, that I'll be able to show what are the set of sufficient conditions to really say, you got it. You answered that first question. Meet this criteria, you'll have your theory of gravity.
So kind of related to that, when you had the classification, it was clear that when neither of the conditions were satisfied, there was no way to find the point.
Yeah.
But when one condition is satisfied, would it be possible, or it's impossible, or it's unknown?
Yeah. So let's go to the. Let me go to that slide just so that I can. I want to show it. Let's do it here because I have the criterions like classified. So this one, for instance, this one only meets one. It only meets the first condition, the existence of the moduli. But it doesn't meet the second one. The second one, in my mind, is more stringent, because if the second one is not met, then I know that I will always have too many states. So I'm kind of trapped. So I think this one, although it meets the first criterion, this one is not going to be what I call holographic.
But sorry. So if you have many states, in that case, it would be that the theory doesn't have a semi-classical limit.
Exactly. It doesn't. It can still be dual to something,
but
it will not.
Einstein gravity.
Exactly. Not the usual Einstein gravity theory. Now, the danger here. So when we meet the second one, what has been fun is that they always fall into this category where automatically both conditions are satisfied. I don't understand why, but every time we put this restriction, then boom, we land with type 1. Now, what we were afraid of was this scenario, where you have very few states from the supersymmetric point of view, but you can't move away. So we were a bit afraid of this. This is also why they're like unicorn for us, because we said, oh, if you only meet this one, but then you don't have anywhere to go, then it's not that it's impossible, but it puts a lot of restriction. We have nothing to say, and then it's kind of like it seems.
You might be already too strong.
No, but the whole spectrum, the non-BPS part, is Hagen-Dorn.
I see.
So I already know that this thing is not, yeah, exactly. So I just know that this thing is kind of a weird thing. So when we haven't encountered any theory that is of this type 4, we tried to prove it, but we actually showed that you can't prove it. Like in a simple, like there's some, if you thought that modular forms were going to be enough to prove it, actually no. But yeah, it's yeah. In any case, we've only found these 3 types of theories, and so then the only ones that meet the criteria and then you might want to call holographic are these first ones. So.
And I think in order to prevent King's Food from taking away our wine, we should thank Alejandra and move over.
How is it going?